Okay, hi everyone. Let's see, a couple announcements. Over the weekend, we posted chapter 26 from the upcoming fourth edition of my textbook, Introduction to Algorithms. Over here are the first three. And this chapter covers the material from my last lecture, today's lecture, and Thursday's lecture. And you're going to find it really helpful for studying for quiz one, which is in just a couple of weeks. And that brings up the second announcement, which is that we've been contemplating, the course staff has been contemplating the ground rules for the quiz. We'll post an announcement sometime this evening, but we've decided some things already. First, it'll be open book, and you can use any inanimate resources, but you may not interact with another sentient being during the quiz. It's as if you're in class. And we're going to take the quiz, or you will, I guess I won't, take the quiz directly using Gradescope during regular lecture on Thursday, October 15th. But we still have some questions. We're not exactly sure how we are going to proctor the quiz. So we're posting a poll this evening to get your input, and we're currently eyeing three options. Option one is no proctoring, the honor system. Option two is that students leave their Zoom videos on with no sound while they take the quiz, and the staff can then observe it, but we won't record anything. And three, the students leave their Zoom videos on and we record them. We will definitely not ask students to put invasive proctoring software, on your machines. Okay, so we're not gonna, we eliminated that. That has too many downsides. And I think at this point, I hope MIT policy is that we won't do that anywhere on campus. But in any case, we're not going to do it. Now, before you send in your opinion, I recommend that the class discuss the options for the proctoring policy on Piazza, and then send your opinion in. I prefer that the proctoring discussion use the public Piazza forum because it'll encourage the entire class to think about this issue. But if you want to talk privately among yourselves, Piazza or otherwise, I have no objection. I mean, talk as much as you want, but I think it's good to have a public forum so that people can talk about the pros and cons, because as we've looked at this, we see pros and cons to each thing. Let me just say a little bit, though, about where I am. I have always taken proctoring seriously. I believe that my duties as a professor include protecting the vast majority of students who play by the rules from the occasional bad apples who lack a social conscience. Okay? And if I do discover cheating among your classmates, please be assured that I will not tolerate it and I will not look the other way. Okay? I want every student to enjoy the confidence that the quiz is fair. So enough said about that for now, but please talk about it on Piazza. Now, let me just also mention that if you expect to have difficulty taking the quiz during the normal lecture time because you're in a different time zone, we'll also provide a form to report your issues so that we can make accommodations. Okay? So, let's get started. We have two lectures this week on parallel algorithm. In today's lecture, we're going to explore a few basic parallel algorithms expressed in Silk and how to analyze them. Okay, we're going to start with an exploration of the simple algorithm that implements parallel loops in Silk. And for that, we're going to look at matrix transpose in this example. So recall for matrix transpose, the goal is to swap Aij with Aji, so that rows become columns and columns become rows. Okay, and we'll make it easy. The matrix is square. It's actually quite interesting to get high-performing code for matrix transpose when the matrix is rectangular. So, but for this, we're going to keep it simple. It's going to be square. Here's the code that does it, or a code that does it. It's a doubly nested loop where the outer loop index I goes from 1 to n minus 1, and the inner loop j goes from 0 to I minus 1. And we've parallelized the outer loop with a silk 4. Now, I remember the first time I wrote this code as an undergraduate at Yale. That was many years ago, let me just say, about 45. And I made both loop indexes go from 0 to n minus 1. Now, I couldn't figure out why my transpose subroutine wasn't being called. I thought I was calling it, but apparently I wasn't because the matrix didn't change. So I felt kind of stupid when my TA pointed out that I was indeed swapping AIJ with AJI, but then I was swapping them back. And it certainly taught me what a triangular iteration space is, as well as what an identity transformation is and how to compute it slowly. So that was one of the first times I realized that if you ask for help, you look stupid. Once. And if you don't ask for help, you are stupid over and over again. And so I learned to get my ego out of my issue of asking for help, because learning is more about rebounding after making mistakes than it is about doing it right the first time. But I digress, I guess. So let's keep going. Okay, so I starts at 1. Because we don't want to bother swapping the diagonal elements with themselves. And j goes up to I minus 1. We want to analyze, so j is always less than I, and that makes it so that, that we never are swapping things back once we swap them. We want to analyze the work span and parallelism of this code, which we learned about last time, but we have parallel loops, not spawns and sinks. Now, as I mentioned last Thursday, the OpenSilk compiler translates loops into spawns and sinks using divide and conquer. So let's see how that works. Okay, so for each silk 4, so if you look at this code, what I've got in the upper left is the original code, and on the right, I've got an implementation. For each silk 4 in your code, the compiler builds a little divide and conquer subroutine like ploop here on the right. You'll notice that we didn't parallelize both loops, just the outer loop. For now, we're not gonna do both loops. We will in a bit. So the ith iteration of the outer loop does I iterations of the inner loop, because the index goes from 0 to I minus 1 for the index for j. The inner loop runs serially, one iteration after the other. But the outer iterations can all run at the same time because the silk 4 makes the iterations logically parallel. Okay. So let's walk through how the compiler transforms the parallel loop. It replaces the silk 4 and body with a call to ploop1, that's at the bottom on the right-hand side, in the calling context. And it lifts the body of the loop into the ploop function. So you can see that the lavender part here, that's a fancy name for purple, is lifted from the original code and sort of dumped into this code, which is effectively what the compiler is working on. And it replaces the serial loop control, that is the silk 4 statement, with this divide and conquer subroutine. Okay, so this is the loop control. Okay, I'm just going to call that yellow. I don't know a fancy word here for yellow. It's not really gold. Maybe it's lemon yellow. The loop control in the p-loop function starts by checking whether there's more than one iteration, okay? And if there is, it splits the range of the loop down the middle, okay, computing mid, and then it recursively executes the iterations in each half in parallel. Okay, so we spawn and then call, the first half and the second half. If there's only one iteration, then it proceeds to execute the I iterations of the serial loop. Okay, so it does that and returns. Otherwise, if there's only one iteration, it goes and it executes this code, which just runs through the row I, runs through all the columns J, and swaps Aij with Aji. Okay, so that's that's basically what it does for its code. Now that we've translated it from the Silk 4 into spawns and sinks, we can look at what the trace would be. And so here's an illustration. So remember that the trace is the DAG, directed acyclic graph, of dependencies among the executed instructions, where we group serial chains of instructions into strands, which are the disc-shaped things in the picture. And we embed the vertices of the DAG into an invocation tree so that the strands in the same function are mapped into the same tree node. Okay. So the question, the Silk 4 actually works with a whole bunch of things that if it can predict what the what things are. It's not as general as it could be. That's some improvements we want to do for the camera. I'm not exactly sure what it does and does not, but you can play with that. Okay, and the parent could spawn all the children directly, but if there happens to be another spawn in the same function, you might get, when you sync, you might sync that as well. So there has to be some level, but you could spawn it without actually calling an auxiliary routine. In fact, that's what it does. This is kind of pseudocode, if you will, pseudo Silk for what's actually happening. Now, the divide and conquer routine, if you look at it, it looks a little bit like fib. It recursively spawns the first half of the iterations, and then it calls the p-loop to recursively as well to execute the second half, and then it syncs and doesn't return until both children complete. So that's a little bit like it, but unlike the fib, the two children have approximately the same size. And by doing this recursively, we get essentially a complete binary tree built up rather than the lopsided tree that fib gives you. So now, if the number of iterations is just one, and it's the ith iteration, say, then it serial executes I iterations of the inner loop. And so the way I've drawn this is that we're increasing the size. I'm sort of showing the size getting bigger to indicate there's more work to do as we go left to right to higher values of I. But you should also realize that the sizes are not to scale, right? The n-1 is not n-1 times bigger than 1. Okay, so let's analyze this now that we understand it. So we'll start with the work. And what do we expect the work to be? All we're doing, so before we try to analyze, let's just say, well, what should the work be? So all we're doing is swapping elements from one side of the diagonal to the other. And there are n squared elements in the array, and all but n get moved. So you'd expect that theta n squared should be the answer. And that's indeed what it is for the serial projection, where we replace the Silk 4 with an ordinary 4. But what about when we take into account all that loop overhead? Okay, what's the work when we take that into account? So you can guess on the Slack channel. So just enter your guess as to what the work ends up being asymptotically. So somebody have a guess? Okay, n squared log n. That's a good guess. N log n loop overhead. N squared log n. Another n squared log n. N cubed overall overhead. Okay, we're just asking right now what the loop overhead is, not so much what the overall. Well, we're asking overall. We're asking overall, sorry. So it's not n cubed overall. So it was n squared. We've got a bunch of okay, n squared overhead. Yeah, so it's actually n squared is what the answer is. Okay, and just shows how good intuition is about these things until you play with them a while. Okay, so it turns out it's n squared, and whoops, I didn't mean to click that. Okay, and you can see that by looking at the leaves first. So the leaves, we're adding up 1 plus 2 plus 3 all the way up to n minus 1, which is theta n squared. And that's an arithmetic series, so theta n squared for the leaves, okay? And that's what you're going to do regardless. But we need to worry about the overhead from loop control. So each of the strands in the internal nodes of the tree runs in constant time. So there are 3 nodes in each internal node, but each of those is just a constant amount of work. And there are n leaves, different size, but that means that there are n minus 1 internal nodes. Okay, that's a basic fact about so-called full binary trees, where every node is either a leaf or has 2 children. There are no nodes that have only 1 child. Then the number of internal nodes in a full binary tree is always 1 less than the number of leaves. Okay, and you can read about why. I have a great textbook I can point you to that really explains this well, I think. It's on page 1180 of the appendix of a textbook that I just conveniently happen to have available. Okay, but you would have to get your own version to look at that. But you can find it on Wikipedia, you know. So there are therefore n minus 1 internal nodes in the full binary tree. Each internal node takes constant work. All the internal nodes therefore take a total of theta n work, which is dominated by the theta n squared work done in the loop body. So the answer is theta n squared. That's the general rule, is that loop overhead adds nothing asymptotically to the work of the serial projection. So you can always analyze work just by looking at what's the work of the serial projection, because the loop overhead is going to be proportional to the number of iterations, and that's it, because of this basic property of full binary trees. Okay, now let's do the span. Okay, so the span. Now this is actually a little bit trickier. So we have a span pole. In fact, we're going to do span. Span has got you'll have even less intuition for until towards the end of the lecture than work. Okay, so so if Tim or Helen, can you put up the span pole? Yeah, there we go. Okay, what is the span of this calculation? Okay, and so let's see here. The span as we go. Okay, that's pretty good. That's pretty good. Good, yeah. So it turns out the majority is right in this case. They're not always right in elections, let me tell you. But in this election, this case, they are right. Okay, and yeah, we can look at it like this, okay? The span of the loop control is log n. We can break the analysis into two parts, loop control and body. The span of the loop control is the longest path from the root to a leaf of the tree and then back to the root. And so the loop control part of it is just the height of a complete binary tree, which is theta log n. And then the worst case span of the body is theta n. We already talked about that, right? So that's just the n minus 1 at the end there. And so the path down to the rightmost leaf and back, total, you end up with theta n plus log n, which is theta n. Okay, so the total is theta n. Okay, it's dominated by the leaf there because the leaf is so big. And so now we can calculate the parallelism. Okay, what's the parallelism? Hopefully this one people get because it's just, so just enter a textual answer here, no poll. How are we doing? Got several people typing, that's good. Okay. Oh, there we go. Okay, order n. Yep, order n. My Slack here didn't scroll. I've got it running on my cell phone here. Didn't scroll. Yep, it's order n, right? It's just the work divided by the parallelism. That's just algebra. And I think most of you wouldn't have gotten into MIT if you couldn't do algebra. Okay. So here's the bottom line. Okay, the parallelism is the ratio of work to the span, and the work is the same as for the serial projection, as we discussed. But when analyzing the span, there you've got to account for logarithmic overhead in the loop control. Now here it didn't make any difference, okay? But you have to, in terms of where the span was, it turned out to be in the body. But it's not always in the body. Sometimes the body will be small, okay? So that's the idea. So let's take a look at a slightly different problem. Okay, this is, again, nested loops for doing transpose. But now I'm going to parallelize both loops. So I have two silk 4s, and then do it. Okay? So what's the work of this computation? Okay, so just answer on Slack. What's the work for this one? Yeah, it's order n squared. Yep, because I just said you just take the serial projection, and inserting silk 4s or spawns or sinks anywhere doesn't change the work. The work is the same, at least asymptotically. It does change the work, just not asymptotically. Okay, so it's n squared. Okay, but what about the span? Okay, so for spans, we're going to take a poll. Okay, what's the span of this computation? Okay, so span poll. Here we go. Same answers as before. Get used to them. Got log n. We got some diversity here. That's good to see. Okay, so it looks like log n is winning. So let's see. The span of the outer loop control is order log n. And for the inner loop, the maximum span is going to be log n because the first iteration, when j equals 0, that has very short span. It just does one thing and returns. Okay, but the last iteration is going to go all the way up to I, so it's really log I, and the worst of those is going to be when I is n minus 1, so it's order log n, and the span of the body here is just theta 1. So if the outer loop is log n, and the inner loop is log n, and the body is order 1, constant work. Okay, so the total span is then order log n. Now, When I first did this, I said, wait a minute, why isn't it log squared n? After all, it's a nested loop, etc. And that's the next thing to sort of understand is the spans of nested loops add, they don't multiply. So we're trying to figure out the longest path. And we have a complete binary tree for the outer loop. So let's imagine this is the binary tree. So the root's up here and the leaves are down here. And off of each leaf hangs another complete binary tree of various sizes like this. Okay? So that gives us n inner loop trees on the second level of these trees. Okay? And therefore the longest path is going to be going down, 2 levels. Well, that's just adding the spans. It's not multiplying them because each one is a separate path. Okay, does that make some sense? Okay, so the spans add when you have nested loops. And then the parallelism, here is just the ratio. Not too hard. I think at this point I don't need to quiz you on your algebra. It is n squared over log n. That is lots of parallelism, okay? That doesn't mean the code will run faster on a parallel machine. We're going to see some examples where we need to worry about whether our base case is large enough that we're actually doing serious work, on the loop body. The serious work is all in the loop body rather than spending our time in loop control, okay? So let's do a quick sanity check here, okay? The trace has a tree with log n levels for the outer loop and log n levels for the inner loop, okay? And how many internal nodes are there in the tree? Okay, well, we can figure that out by realizing the tree depth then is 2 log n. So essentially, the number of leaves we have there is n squared, okay, because it's 2 log n. It's 2 to the 2 log n. That's just n squared, which is then approximately how many leaves there are. And so there's going to be one, essentially for each of these, there's going to be, one for each internal node, and then there's going to be one for, there's going to be, n minus 1 in the worst case, but in general, there's going to be order n, and the size of that, because of this full binary tree property, the number of internal nodes is going to be almost n squared. Okay, so they're going to be almost n squared spawns and returns. And so even if the spawn were just an ordinary function call, that would be a lot of overhead for each individual swap. A swap is really fast, okay? And a spawn here in OpenSilk, and this is just our beta that you're working with, and so it's not as tuned up as we would like to get it, but right now I think it's around 10 times the cost of a function call when you run it serially. So you can see that's a lot of overhead. It's 10 times the cost of a function call, and the function call is going to be a lot greater than the swap. So there's a lot of overhead in the loop control. Okay, so that isn't so good. So we'll look to see how we address that issue later. We've got a lot of parallelism, but that's not so. So we're gonna see how to get rid of that later. Okay. But here's a different problem that we can use to better understand the problem of loop overhead, and then we'll be able to see what we do in general. It's a simpler problem. Here we're just implementing a vector addition with a simple loop that adds one array B into another array A in an element-wise fashion. So it's a Silk for loop, which means it's okay for Silk to run all the iterations in parallel. Okay? And here's an illustration of the trace we'd get when we execute this code. Okay, so let's do an analysis here, okay? So the work, well, there are n total iterations, so the work is order n, okay? Just ignore the Silk for, turn it into an ordinary for loop, that's fine, okay? And now what's the span? Oh, time for another span poll. Okay, so what's the span of this one? Okay, looks like log n is winning. Yep, there's a good reason it's winning. That's the answer. Okay, the span is just proportional to the height of the tree, which is order log n. It goes down, goes back up, and it does constant work at the leaves. Okay, and so the parallelism, which is the work-span ratio, is order n over log n. So we're getting good at this. That's pretty clear, okay? But let's look back at the work, and the trace can help us to understand the overhead. There are n leaves and n-1 internal nodes in the loop control tree, which means that there's practically one spawn for every iteration, okay? Even if the spawns were just function calls, as I mentioned, the overhead would be onerous, to say the least. Okay, it'd be pretty heavy overhead. You would really see a slowdown, especially if you executed the Silk code serially. That would not be good. Silk would not get a good reputation. I would like Silk to have a good reputation, especially OpenSilk. Okay, so what do we do? Well, we can use a Bentley rule. Okay, so Bentley rule, one of them was get rid of function call overhead by coarsening the recursion. Okay, and so that's what we want to do. And we can do that because Silk makes coarsening the parallel loops easy. Okay, in particular, it allows you to specify a what's called a compiler pragma and give a grain size. And a pragma is just a suggestion to the compiler, okay, which the compiler is free to either do or not do, but of course we want to listen to the hints. And this suggests that it shouldn't execute just one iteration at the base of the recursion. It should execute G iterations at the base size. Okay, and so in the recursion, whoops, it's supposed to be called p-loop. Sorry about that. I called it recur here. So in the base of the recursion, there are some, instead of going down to high greater than low plus 1, we go to high greater than low plus G. And now we go through and set all of the iterations of the loop to do the vector addition there. Okay, and then we recur on, and then the call is to recur on 0n here, of course. Okay, so if you don't specify a grain size, Silk makes its best guess. Okay, and it usually does pretty well. But here we're going to look at what happens when we express it explicitly. Okay. So let's take a look at what that does, the impact of grain size on performance. So basically what it does is, what we're going to do is it's going to execute G iterations in each leaf. And let's so that we can get a sense of this, I be the time for one iteration of the loop body. Okay? You're just fetching the single elements of A and B from memory, adding them together, and storing back the result. In practice, you could imagine I would be pretty small because the compiler and processor can vectorize and prefetch and speculate to really make a simple loop like is going on in the leaves here run fast. Okay, but we'll just use this approximation that's G times I right now. Okay, so it's going to be G times I because there are G iterations in the base case. So now let's see. Let's S be the time to execute a level of the recursion. Okay, S standing for spawn. And I may call it spawn, but it's really the dividing up and the spawn and the return. Okay, so I'll just say that to keep it simple. Okay, so now we can derive an expression for the work. And here's what the expression is. So what's going on here? Okay. So let's see. Let's take a look at the first term, which is n times I. It's just the total number of iterations. And that makes sense if the total number would be n, okay, because even if we're executing in groups of G, we're still doing a total of n iterations. Okay, so we have n over G groups of size G. So it's still n, okay? And we have n over G leaves, so the total work then is going to be for the work is going to be, they're n minus 1. There's going to be n minus g minus 1 internal nodes, because the total, by the full binary tree property, the total number of leaves is n over g. Okay, and so each of those is going to cost us s to execute everything in it. Okay, so that's the real work there. And since we have, if we look at the total work here, okay, that this formula gives, it's pretty clear that if we want to minimize the work overhead, we should make g be as big as possible, so that the second term, which is the work overhead term, is as small as possible. Okay, we'll come back to that in a moment. We like the first term, the n times I term, okay, because that's real work. But we don't like that second term because that represents just overhead. And we'll come back to that in a second. Okay, let's take a look at span. Okay, I think we'll forego a pole this time. It's not just a function of n, it's also involves g. So we need to find the longest path in the trace. So that happens to be this path here. Okay, it's just down the tree on the rightmost path, through a leaf, and back up the tree. Okay, the contribution of a leaf to the span is just g times I, no big deal, because we're executing each of the g iterations in a leaf serially. Okay, and then going down and up the tree goes through one frame per level of the tree, part of it on the way down, part of it on the way back. Okay, and the height of the tree is log base 2 of n over g, and each frame costs s, so we get the second term. Okay, and now we want to minimize this expression, okay, so that we get the most parallelism, okay, and that way, and so if we want to do that, to minimize it so we get the most parallelism, we should pick g to be as small as possible. So we have a trade-off. The work wants it to be as big as possible. The span wants it to be as small as possible, okay? So what's a happy medium here? How can we resolve this dispute between work and span? Okay, let's take a look at the work expression. Okay, now observe that there are diminishing returns to making g be big. Okay, as we increase g, once the second term becomes smaller than the first term, so as g gets bigger, the second term gets smaller, and once it becomes smaller than the first term, continuing to make it much smaller doesn't happen as much. Okay, so let's throw, so that minus 1 is an annoyance, so let's just get rid of that because it doesn't really matter. Okay, and now, so if I'm going to try to optimize this, okay, I have n times I plus n over g times s, and they both have n, so n doesn't really have any bearing on which term is larger. Okay, so we can basically get rid of that as we're looking at the optimization. And now what we want to do is want g to be sufficiently smaller, so we want I to be bigger than s over g. That's basically what we want. I should be bigger than s over g, or equivalently, g should be bigger than s over I. That's algebra, okay? So that the first term dominates. Okay, so we want g to be sufficiently larger than s over I to minimize work effectively, but we also want it to be as small as possible so that we have parallelism. Okay, so we might pick b to be, for example, 10 times s over I. Okay, as small as possible so we have enough parallelism, but large enough that the work overhead here is only a few percent, at most 10%, say. Okay, if you wanted it bigger, you could make it be 20 times or whatever. Okay, and then for the parallelism, okay, we get when you do that, okay, you get that the parallelism is going to be the n over log n we originally analyzed, inflated by a few percent, but basically derated by how much more expensive the spawn overhead is compared to the execution of an iteration. Okay, so we have so we have the so we have essentially the answer derated by, and that's interesting to see what's derated. It's the ratio of this of the spawn cost to the iteration cost. Okay, so so we could even reduce it, handle things more. You get more parallelism if S over I is smaller. Okay, now it turns out the automatic scheme that I mentioned, the Silk runtime system, says if you don't use a fixed value for G, works something like this. It picks a grain size that produces about 8 times more parallelism than the number of processing cores you're running the computation on. And that's usually good. Almost always you want to leave it automatic unless you want to experiment, okay? The automatic scheme is going to be perfectly good. Of course, my research group is currently investigating even more clever ways to reduce loop overhead. And let me just say, we're always looking for motivated UROPS and MEng students. Good. So now let's look at a different implementation based on a similar idea. Okay, so instead of a divide and conquer Silk for loop, this implementation directly spawns a bunch of parallel iterations of size G, which is the grain size here. Okay, so in OpenSilk, it turns out you can spawn a statement block. You have to be a little bit careful because now your variables are free and they're going to be evaluated after the spawn rather than beginning it. So you do have to be careful. It's safer to spawn an actual function. Okay. So the outer for loop here jumps through groups of G iterations and spawns an inner loop to add up the individual elements, the G elements in each group. And when all the groups have finished, it syncs. Okay, so that's kind of what it's doing. Okay, so here's a trace. Okay, so let's figure out the loop overhead for this version. Okay, so we'll start by doing the easy stuff. I always do the easy stuff and then generalize because the easy stuff may be hard enough. And then once you get insight into the easy one, now you can try to extend it to the harder one. Okay, so let's assume that G is 1 here, and let's take a look at the work. Okay, so that's going to be, well, it's the same. It's N, right? Because it's the same as the serial projection. I don't know why I keep asking. I should just say it all the time. Okay, so what's the span here? Okay, G is 1 now. What's the span? Time for another poll. What's the span here? Yeah, we got order 1, we got order N. Okay, so it's adding up. Get your value in quickly. Okay. Yeah, it turns out it's order N, okay? Yeah, it's not very good, okay? And here's the path that does it, okay? So it turns out that horizontal path is order N in length. It's length N over G, okay? And for G equals 1, that's order N. And so this is terrible, okay? The parallelism is just order 1, and we have a technical name for that. We call it puny parallelism. We don't like puny parallelism, okay? We don't like puny parallelism. This is no good, okay? So lousy scheme when N is 1. Okay, sorry, when G is 1. Okay, so let's go on and take a look. That was for G equals 1. Turns out this isn't necessarily as bad as we can see if we try to figure out what's a better value for G. Okay, so we'll analyze it in terms of G. So now the work, well, that hasn't changed. That's theta N has nothing to do with G, at least asymptotically. Okay, and now the span, okay, let's do a slack poll. Oh, no, let's not do a slack poll. It's too complicated. Yeah, I would do this in class, but Zoom is not a good place to do this. So, and it won't be a poll anyway. So, so here it is. It's a formula. It's G plus N over G. And it's basically this, it's basically, oh, I've lost my picture. It's basically, if you take the path that I showed you before, it's N over G for the horizontal part, and it's G for the leaves. So the total ends up being theta N over G. And there are two terms which I can minimize by setting them equal, which says that I should pick g as the square root of n. So the span in this case, if I pick it g optimally, is the square root of n. Okay, I get, and so what parallelism do I get? Then I just get the ratio, which is square root of n. So the answer is that it's not as bad as it looked at first. It's not as asymptotically good as the theta n over log n we had before, but it's not bad. It's getting you some, it's getting you some parallelism, square root of n parallelism, if you pick the grain size sufficiently large. Now, it turns out the I equals j and the j plus statements don't create a race, because the way that Silk does the loop, it creates a private value of the variable for each iteration. But it's a great question. Okay, great question, great subtlety there in the code. Very good. Okay, so here's a potential quiz question. I'm going to leave this for you. Okay, we have two versions of the same code, but I'm going to skip it and let you try it out on your own. It's a good practice to test your understanding, and I think over Zoom it's not going to be really effective to run through it in real time. It'd take too much time. We have other fish to fry. Okay, so let me get to, let's quickly get to performance tips. Okay, so here are 3 performance tips that you can get from this. So you want to minimize the span to maximize parallelism. Okay, you try to generate 10 times more parallelism than processors for near perfect linear speed up. If you have plenty of parallelism, you try to trade some of it off to reduce work overhead. Okay, and use divide and conquer recursion or parallel loops rather than spawning one small thing after another. So you do the first thing rather than the second thing. Okay, you do the Silk 4 rather than spawning things off one at a time. Although sometimes the Silk compiler is clever and it can actually see the second one and optimize it to be the first. Okay, so it's very clever that way sometimes. Okay, here's 3 more. Ensure that the work per spawns is sufficiently large, and if need be, coarsen it using function calls. You can also use inlining near the leaves, or even writing a special thing rather than spawning. You should generally parallelize outer loops as opposed to inner loops if you're forced to make a choice. And watch out for scheduling overheads. It's generally better if you have 2 loops and you could parallelize either one to parallelize the outer one that's big, rather than, so here I've got 2 iterations with an inner for loop with n iterations rather than an outer loop where I have n little iterations and each one is spawning off this teeny tiny amount. Okay, so do that instead. And for this last example, by the way, the Silk Scale Scalability Analyzer is your friend. It will show a high burden parallelism, which is like parallelism, but it accounts for scheduling overhead. And that's described in the SilkView paper in the supplemental reading. And that can help you a lot as well if you look at how that's done. Okay, I want to move on to some real algorithms now. So let's look at a problem I think you've seen before. It's called matrix multiplication. Okay, so here's the formula again. I think everybody should know that at this point. This will actually not be the last time we're going to look at matrix multiplication. It's a great didactic example. Okay, so here's one way to parallelize it. We have triply nested loops and we parallelize the outer 2 loops. Turns out that parallelizing the inner loop isn't quite as straightforward because there's a race condition when you do it. Okay, so what's the work of this parallel algorithm? Well, it's just n cubed. That's the same as for the serial projection, which is just the naive serial algorithm. We already talked about that, okay, earlier in the term. Okay, what about the span? Okay, let's do a Slack poll on the span for this. Let's see what people have learned. What's the span for this doubly nested loop? It goes through the outer 2 loops in parallel and the inner loop serially. So yeah, so the control for the outer parallel loop is log n, and the control for the middle loop is also log n. And then the inner serial loop is theta n. So the majority has it here. It's theta n. Okay, so span is theta n. Okay, and so the parallelism here is about n squared. Okay, so just to get a sense of how big that is, let's assume that we don't have constant factors here. We do, but we're going to just get a ballpark here. Okay, so for 1,000 by 1,000 matrices, for example, the parallelism is about, therefore, 1,000 squared, which is about 10 to the 6th. Now, we may derate that by, I don't know, a factor of 10. Hey, factor of 100. I still have a huge amount of parallelism, okay? And but let's remember that it was theta n squared, because we're going to want to compare other algorithms to this one for the span, okay? And so for 1,000 by 1,000 matrices, you know, our rule of thumb for slackness was you probably wanted 10 times more parallelism than processors. I think we got it covered, at least for the machines you're going to see in this class. And if you were going to do a larger problem, you would do probably do a larger matrix. So there's two types of scaling that people talk about. One is called strong scaling. That says you run the same size problem on bigger and bigger machines. And the other is what's called sometimes weak scaling, where you run a problem where the more cores you put on it, the bigger proportionally you make the problem so that the work per core is the same, okay? And so for you know, larger and larger machines, the idea is you want to use weak scaling because you're talking about bigger and bigger problems that you can take on. But in any case, we got oodles of parallelism here, okay? That's good. Okay, so guess what? You can do matrix multiplication in a divide and conquer fashion. And one of the reasons for this, as we're going to see later, is that it uses cache more efficiently. Okay, so we're going to do that in a couple of weeks. Okay, in a few weeks. I think right after the quiz we do it, actually. Okay, so so this is a divide and conquer scheme, and you know, I think this scheme is a theme. So the idea is to suppose we view C as being composed of 4 n over 2 by n over 2 submatrices, and of course we can do the same for A and B. So then the product of A and B can be written as the sum of two other submatrices. Okay, it's two other, matrices that are n by n, where each of those matrices consists of 4 submatrices, you know, 4 submatrices, and each of the submatrices is the product of 2 n over 2 by n over 2 submatrices. Okay, so that suggests a recursive algorithm for matrix multiplication. Okay, so we've got 8 multiplication of n over 2 by n over 2 submatrices and 1 addition of n by n matrices to compute it. Okay, but how in software are we going to divide up the matrices? So it turns out matrices, as you may recall, use a row major layout, which you should be familiar with from Project 1. And suppose what we want to do is we would like to do index calculations rather than actually having to move the submatrices around, okay? So things can be stored right in we can point right to a submatrix. But a submatrix is not a contiguous part of a larger matrix. So here we have a submatrix A that has a contiguous, that's part of this matrix M. The M is what's stored contiguously, but A is going to be jumping around as it goes from row to row. If within a column it's consecutive, but within a row it's going to jump. Okay, so suppose that we know the index of the upper left corner of A. Okay, how do we index the ij element? So the idea is that we want to go down I rows and over j columns. But the start of each row is n sub m elements after the start of the previous one. It's not n elements ahead, okay, the way that this is stored as a submatrix. So the index of the ij element is A of n sub m times I plus j, not n n times I plus j. So notice the row dimension of A doesn't enter into the calculation, and neither do the column dimensions, just the row size of the underlying matrix. So that's the important thing to understand. So now we can look at our dividing of an n by n matrix. And remember, we're assuming a power of 2 into 4 n over 2 by n over 2 submatrices. Okay? So we want to figure out where each of the 4 submatrices start, because we don't want to incur the overhead of moving the submatrices around. Okay, so A00 is pretty easy. It starts the same place that A does. No problem. Okay? The next one's a little harder. Okay? So A01, okay, that's the upper right one, starts in the middle of the first, which is to say the 0th row, which is just n over 2 elements from the start of A. So it's just A plus n over 2. Okay, that wasn't so hard. Okay. Now A10, the lower left one, starts at A, but now I go down n over 2 rows, and each n over 2 row has n over m elements in it. So you have to multiply n over 2 by n sub m. Okay, and for square matrices, that's going to be, for power of 2 matrices, that's going to be particularly fast, because that's just a right shift that I can do. Okay, but always be careful right shifting signed numbers. Okay, you want to be careful, because if it's a negative number, that gives you undefined behavior in C. And undefined behavior, UB, lets the compiler do anything it wants, including give you wrong answers without telling you. Okay, so that gives us that one. Then the fourth one is A11. Now we go down n over 2 rows, so we have to multiply those by the n sub m by n over 2 and over n over 2 elements. And so if you do the distributed law of multiplication, you get this formula. Okay, not bad. Okay. Now we can generalize that by saying, okay, for R and C, each being 0 and 1, okay, it's always the case that A sub RC is A plus R times the underlying row size plus C, that quantity times n over 2. Okay, so that's going to be a general rule that we have that lets us encapsulate that. Now, in fact, you would hope that if you're going to actually use this in your code, the compiler will see what is constant here if you're giving zeros and ones, and will do an appropriate common sub-expression elimination, so it doesn't have to go through the entire calculation even for A00. But it may help us to write cleaner code, which we'll see here. So here's the divide and conquer code, MMDAC. Okay, so let's just walk through this. We have the familiar restrict keyword. This lets the compiler assume that the input matrices are not aliased, so it optimizes better. Then for each recursive call, we need to know the start of the 3 submatrices A, B, and C, as well as the row length of each of their underlying matrices. So these are the row sizes that I'm highlighting here. Now, if all the matrices had the same underlying row length, you could only pass one value for the row length, or keep it as a global. But here, we're not going to make that assumption, because you're going to see that as we dive into the recursion, the matrices don't all have the same row length all the way through. Okay. We also need to pass the side length of the 3 matrices. Okay, n in this case. Okay. Now, we're going to compute the product of A and B, but rather than storing the result into C, we're going to add it into C. So if you want to compute C equals A times B, you need to zero C first. Okay, but zeroing only costs n squared work, which is much less than the n cubed work of the multiplication, and you can do it in parallel if you really want to. Okay, if it's not a bottleneck, So, okay, so we're going to add it in. Okay, so the idea is, this asserts that n is a power of 2 using a bit trick. It probably should have a comment in it. Shame on whoever wrote this code. I'm always shaming myself, okay? In fact, it's a bit trick to test whether n is an exact power of 2, and you should be kind of familiar with this idea of ANDing n with minus n, okay, because it just extracts the low order bit, and if in fact that's the whole thing, then you say it's power of 2. Okay, another shame. This actually has a minor bug because the test will pass even if n equals 0. So you probably should have a test that n is positive in addition to this assertion, okay? I love assertions because, and I like the TB assert package. That's really great. I like assertions because it doesn't cost you anything at runtime. You just run with its asserts off and you get fast code because it doesn't do this stuff. Good. So then we go on. We're going to coarsen the leaves of the recursion to lower overhead. So I'm going to go only down to threshold. And if I hit something that's less than or equal to the threshold for whatever I pick to be a reasonable number, we're going to call a base case routine called MMBase. Here's the routine. Okay. It basically just does the ordinary triply nested loop, which most compilers optimize really well, but it understands that the matrices it's multiplying are submatrices within some array, and so it does the appropriate index calculation. Okay, so it treats the two-dimensional array as a linear array and does the index calculation manually. Okay, so pretty. So now we allocate a temporary array D to hold for the recursive submatrix calculation. So what's going on here? So let's see. So we're going to generate 8 submatrices, 4 for each 2 by 2 for each of the 2 n by n matrices that we need to add together. One of the matrices can be the output matrix C. Yay! But we need a place to store the other 4 submatrices, in that other. And that's what we're going to use D for, okay? And we're going to check that our malloc worked, okay? Otherwise, we have a bug. Okay, so the temporary matrix has row size n. Now notice this is n, not n sub m, and so that's where we might break the assumption that all matrices have the same underlying row size, because it's not true for D, okay? Then here's a clever macro that helps us to write clean code. Okay, this macro calculates the start of submatrices according to the formula we derived early. And the way it works is you give it the matrix name M, and then a 0 and 1 for each of R and C, and it figures out where the start of matrix M sub RC begins. Okay. Now, it's using this double hash, which is a really clever and dirty C preprocessor trick. This is the token pasting operator. And what it lets you do is glue together the n sub with the matrix name that's passed. So it turned out to be really important. I called it n sub D and not something else, because I'm going to therefore be able the n sub D that I defined in the previous statement is got to look exactly like n with a sub whatever the matrix name is, okay? Because we're going to use that here in the code, okay? So it glues those two things together, and so for example, if you pass C as M, it creates the token for n sub C, okay? And then performs the calculation. Without this macro hack, the code really can become kind of messy to have to write and get correct. Okay, with this, it makes it really simple and clean, and it's probably a good use of macros, even if it's a little tricky. Okay, if you're going to use something like this, you should talk to your project teammates. I swear, it's like, don't surprise them with this kind of stuff, right? And document it well, better than what this code is. Don't do as I say, not as I do. Okay, so now we have 8 recursive calls, which we spawn, except for the last, which we'll call. You can actually leave in the spawn, and the OpenSilk compiler is smart enough to optimize it away. Earlier compilers didn't do it, but our compiler is really, really good. Okay, so you can see that the results from the first recursive spawns, the first 4 recursive spawns are stored in C, and then the second recursive calls, they're all stored in D. Okay, and you can see the 0s and 1s going up there to form the C sub 0, 1, 0, 0, C sub 0, 1, etc. that we have before, and then we do the same thing for A's and for the B's, etc. Okay, so they're all stored into the right place, and the last 4 stored into D. Okay. Okay, now after the 8 subproblems are complete, we're going to sync to, before we add together the 2 matrices C and D. And the way we do that is we add the temporary matrix D into the output matrix C, okay, using this subroutine, which basically just goes through and does a parallel add using the appropriate indexing, okay, to add everything in parallel. We're going to come back to this code, but it basically just does a doubly nested silk4 to do the element-wise addition. Okay, and then because we don't want to have a memory leak, we free D, and that's it. Okay, so we want to analyze that, but I just want to, so clean up and return here, yep. So to analyze the work span and parallelism, we're going to want to analyze divide and conquer recurrences. And it helps to write down the divide and conquer recurrences to describe, and once we write them down, we're going to need to solve them. And for the most part, we'll be able to solve them using a technique called the master method. Now, you probably know the master method, or Akrabazi, or something from 6006, or 6042, or 6046, or something equivalent algorithms course that you've taken. But you might want to pay attention because it never hurts to review. And if you don't know how to solve recurrences, you're violating the prerequisites for 6172. And you'll really want to pay close attention, or else drop the course now before it's too late. Because we're going to see these. Okay. So the master method, which I'm going to review rather quickly because I'm kind of assuming you've got it, but I'll leave it in the notes, applies when you're faced with a recurrence of the form, T of n equals A, T of n over B plus F of n. So F of n is usually the running time of a recursive program. And usually the recursives should be grounded in base cases, but we usually omit an explicit statement of the base cases and just assume that the running time is constant for constant size inputs. Okay, so how do we solve this? Well, the master method provides a cookbook scheme that you can memorize, a recipe, and to solve them in your head. Okay, so let's first take a look at the recurrence, and then we'll learn the master methods. So this is what I think I'm going to skip over. You basically can understand it by looking at at expanding the recursion, and then what you do is you add up the levels, okay, and then you look at what's the height, which is log, it turns out it's log base B of n, and you have a thing, so the number of leaves, it turns out, is a to the log base B of n, and that's the same as n to the log base B of a with a little bit of algebra, okay? And then we have the idea of the master method then is to look at this, and what you're doing is looking at the top and bottom of this stack. Okay, so the bottom has n theta of n to the log base B of a, and the top has f of n. And we're interested in basically 3 cases. Case 1 is when things are geometrically increasing, and there's some technicalities there because it has to increase by the, you have to have f of n increasing by be at least a polynomial n to the epsilon amount growing more slowly than n to the log base B of a. Okay, and since it's geometric, the answer ends up in this case being log base B of a. And then similarly, for case 3, it's just geometric going the other way. And once again, there's some technicalities, including a race condition, and it turns out the answer is sort of f of n. And then the answer for the third one is, well, they're about the same time, in which case it either is the same at every level or it increases arithmetically. So arithmetically with 0 rather than arithmetically with 1 or whatever. Okay, and there's some details here. F of n is log to the base b of n log to k for some constant k, and that gives us this answer to the recurrence. You basically tack on an extra log. Okay. And so here's a cheat sheet, and you can go to this web site and see the cheat is tinyurl.com/mm-cheat. And I'll let you, if you want, you can call that up right now. Maybe one of the TAs can just type that into Slack so people can just click on it, or into the chat, whatever, so people can just click on it. And so tinyurl.com/mm-cheat, and you can then, if you need this as we're going through the rest of the lecture, you can use it. Okay, I once again gave a quiz. I'm going to let you do that on your own just to make sure you're fresh. One thing you should know is that sometimes the master method doesn't apply, and that there are more general but somewhat more complicated solutions. Okay, let's go and do our analysis, because that's what we really want to do. Okay, so we start by looking at the addition subroutine. I sort of said, you know, for the addition subroutine, we're just going through and adding up the doubly nested loops, you know, doing them as a SOAP4. That's right. So the work is just the serial projection. At this point, you should know that's n squared, I hope. If not, you know, then learn it. No shame in having to learn stuff. Okay, as I mentioned. What about the span? Let's do a poll for the span of this. See what we get. Okay, so we're getting everybody saying, so far saying that it's log n. That's right, we'll move along. Okay, yeah, the two nested parallel loops each have logarithmic overhead, but they add. And each iteration of loop body does constant work. We saw an example almost identical to this, you know, with a little bit of difference. So the total is order log n. And then we're not going to calculate the parallelism. You can look at it, but we want to just use those values for work and span. Okay, oh yeah, so maybe we should remember what they are. So just remember here these bounds. For the work, the work for matrix addition is theta n squared, and the span is theta log n, because those will come in as we analyze things. Okay, so here's our matrix multiplication. I got rid of a lot of the constant time stuff just to make it fit on the slide. First, the work. Okay, well, we know what the answer should be, but we haven't even analyzed what the work of the, you know, it's not the loop algorithm, but we're hoping it'll be n cubed. But let's instead write a recurrence, and I claim that the recurrence is 8m sub 1 of n over 2 plus the cost of the addition plus 1. And where does that come from? Okay, well, we had 8 recursive calls to MMDAC. But one of the things that's fun about Spawn is that it's, well, first of all, let's plug in for A1 of n. Sorry about that. We plug in first for A1 of n. That gives us, that's order n squared, and we can suck up the constant time into the order n squared. So this is really the recurrence that we want, okay? And so, so let's just take a look at what we're going to get here. This is a classic master theorem recurrence, okay? Where are we getting the 8m of n over 2? Somehow I lost a thing here. Well, we're getting 8 because there are 8 spawns, right? And okay, so good enough. So so we have this is case 1. Oh, I was going to do a poll here. Okay, so it's case 1. I already gave it away. Okay, so because n to the log base b of a is n to the log base 2 of 8, because A is 8 and B is 2. And log base 2 of 8 is 3, so that's n cubed. That's much bigger than theta n squared, so the answer is just theta n squared. Sorry, I forgot to give you guys a chance to warm up on these. Okay, let's do the span. Okay, and let's do another span pole now. Okay, what's the span of this computation? This one takes a little bit more thought. So log n's. And n log n. Yeah, this one takes more thought. There we go. Somebody gave us a log squared n. Okay, well, let's see. Okay, so what we're doing is we're taking the maximum of these things. So the recurrence that we're going to get is going to be the worst of those, which is just 1. We only have to pay for 1. That's the beauty of span, is you don't have to pay for everything that isn't. And it's going to be the worst of these, but they're all symmetric, so it's just one of them. So we get then, it's the span of m sub infinity of n over 2 plus the span of the addition plus 1. The span of the addition was log n, so that sucks in the theta 1. And there is a, so that gives us the this recurrence. And this recurrence is case 2. Oh, I did it again. I was gonna, okay. Is case 2. Okay. N to the log base b of a is n to the log base 2 of 1. That's 1. And f of n is n to the 1 is f of n is n to the, excuse me, that should say 0, shouldn't it? Okay, that's a bug. That should say 0. Sorry, n to the log base 2, no, it should say 1. N to the log base 2 of 1, that's n to the 0, that's 1. So then n to the log base b of a, that's 1. The whole thing is 1 times log n. That's just log n. So log n and comparing it with log n, they're the same size. So I tack on the extra log, and I get log squared n. Okay, so that's the span for that. So see, you got, it's not quite so straightforward. This time majority got it wrong. Okay, no shame in that. Once again, it's like, let's all learn. Okay, if I had to guess, I wouldn't have guessed log squared n, I'll tell you. Okay, so the parallelism in it is now the ratio. That's then n cubed over log squared n, and if we do our thing for 1,000 by 1,000 matrices, we now have parallelism of 10 to the 7th, and 10 to the 7th is much bigger. That's even more parallelism than we got with the parallelizing the loops, which was only 10 to the 6th, but still way more than we need. So can there be something, such a thing as too much parallelism? And the answer is, yeah, there can be. Okay, and when we have way more parallelism we need, we can trade it for things we care more about, like serial running time, that is work, okay, which will help things overall in practice. Okay, so here is this is where we're running into trouble. We have these darn temporaries. We had to keep allocating and freeing, and we'd like to get rid of it. And that invokes kind of another Bentley rule, which is you can sometimes minimize storage to maximize performance. Sometimes the other way around, but here we're going to minimize storage. Let's get rid of this allocation. That was ugly to begin with. Okay, let's just reuse C somehow. Okay, and so we're going to trade it off for the ample parallelism for less storage, and still end up with plenty of parallelism, we hope. Okay, so we can't just use C wherever we've used D, because if we plugged in C lower down, we'd create races, because the first four problems, subproblems, are all independent. Those are okay with each other, but the second four would, collide on C. Okay? But here's a clever idea. Let's just spawn off the first four, and then let's wait for those to be done, and then do the second four. Okay? So we'll do four subproblems, sync, and then the rights of the second four subproblems won't race with the rights of the first four subproblems. And since we're directly adding into C, we don't even have the extra auxiliary function for adding matrices. Okay, we just go boom, right into the answer. Okay, we do the first four, they write into the answer, adding it in, and then the second four added in. Okay, so we do four subproblems, sync, and then do four more subtries. Now we're putting in synchronization, so that's going to, allow us to reuse the C matrix without racing, and we avoid the temporary, but our code is less parallel. But what does it cost in parallelism, okay, to reuse C without racing? Okay, so what do we think? Does it cost, maybe it's free. Maybe this is not a problem. This is not where we run into problems. What does it cost us? Okay, so first we'll do the work. So the work, practically the same recurrence. We don't have to do the add, so we actually have a theta 1, but theta 1, theta log n doesn't matter. It's still case 1 of the master theorem, and we have theta n cubed. The n to the log base b of a dominates. Okay, now the span. Okay, so let's do a poll. Last poll, I think. Okay. Last poll. Can we get the last poll? Slack poll, please. There we go. Okay, so it stays at log squared, some people think. Some people think it goes up to n log n. Some people think it's order n. Oh, this one we're getting a good divergence. Okay, better finish up here. So, okay, good to take a guess. Okay, good to take a guess. Okay, let's take a look. So here we have the max of two groups, which is what we have to worry about. Okay, and so each group ends up having its own max, which, since it's symmetric, is the same as doing one. And so we end up with two problems of half the size plus order 1. Okay, and that ends up being case 1, which is n. So the span is actually order n. Okay, so the span is order n. Good guess for the people who made it. Okay, the parallelism of no temp multiply, therefore, is, order n squared, which is basically what it was for the doubly nested outer loop. Okay, but as I mentioned, it's got better cache behavior, and the constant factors are really very good for this. Okay, so that's for parallelism. We have basically order n squared parallelism as opposed to n cubed over log squared n for the one that was actually more efficient. And for 1,000 by 1,000 matrices, okay, we got parallelism around 1,000,000. Okay, no problem. Okay. And it turns out this is way faster in practice because it's much less overhead. We've traded, all that excessive parallelism. The key thing about parallelism is you just need to get it big enough. And if it's big enough, then the threshold, you win. Okay? You don't have to make it keep getting more parallelism. Okay? But something like 10 times. So next time we'll analyze more parallel algorithms, including parallel sorting. And good luck on your screensavers. And once again, I'll hang around to answer questions or take your abuse. Okay.